Hello everyone, welcome back. In this video, we're going to talk about kinetic energy, and I'm going to start by deriving this equation. Now, to be honest, for a good portion of the derivations we've done this course, you probably don't have to memorize the extra derivations, but these energy derivations are ones that you need to know because their connection to the work equation, which is what we're deriving them from, is pretty important conceptually. So to start, let's bring up the first equation we actually know, which is the transfer of energy to or from the system, which of course is the work equation. Work is force parallel times displacement. And a quick note, this force parallel is an average force and is very often also the net force on the object. And if you're looking for total transfer, this also needs to be the net force on your system. So we're going to keep our system very simple. Our system is just going to be this cart. Someone is going to push this cart to the right. It will start at rest and will reach some kind of final velocity. And of course, the two vertical forces on the cart are going to cancel to ensure that this is my net force. Okay, to start out, since force parallel is a net force, I'm going to rearrange second law. So force is mass times acceleration times delta D. Now the next thing I'm going to do is borrow from our previous equation list. I'm going to borrow our acceleration equation here, and I'm going to borrow this first kinematic equation. So I'm going to do a substitution for A and delta D. Mass stays, acceleration is Vf minus Vi over delta T, and displacement was 1/2 Vi plus Vf times delta T. Now, a few things happen here. Number one, this cart started at rest, which means my VIs are 0. Two, I have time here and here, so they cancel out. Now I'm going to do a little rearranging here. I'm going to take this half, I'm going to put it first. I'm going to take the M, I'm going to put it second. What I have left is VF and VF, which means I'll get VF squared. So if force parallel was exerted on this cart for a certain distance, delta D, and from rest obtained a final velocity, this would represent the amount of energy that was transferred into the cart. And this, of course, would have transferred in as kinetic energy. So this is how kinetic energy can be derived from work. So our kinetic energy formula is going to be 1/2 mass times the current velocity squared. When I say current velocity, I mean this is an instantaneous velocity. Notice I have no subscript here. So at the beginning of the problem, this would be velocity initial. At the end of the problem, this would be velocity final, which is typically how you're using it. Now, for the most part, if you're only doing kinetic energy, this is it. This is the formula. You're going to rearrange it. You know kinetic energy, you know mass, search for V, or maybe you're missing mass, whatever. However, outside of the first introduction, there are almost no energy questions like that. The real energy questions come with the transfers, which is what we're doing later. But for now, let's do a simple problem. A 5 kilogram physics cart is pushed from rest with a force of 4 newtons for a distance of 2.5 meters. What is the velocity of the cart after this period? So again, I have my cart, it's being pushed to the right, I have a displacement to the right, velocity initial is 0, and velocity final is what we're looking for. My givens, I'll put over here. I'm going to add one more thing. Now, what this is and why I'm using it, I will discuss a little later, but the basics is I'm going to make a visual representation of my energy transfer. I definitely have work being done because I'm exerting force on the cart, the energy is coming from me, and I am not in the system. Speaking of, my system is just the cart. So the energy transferred from out to the system is all going to become kinetic energy here. Work is force parallel delta D. 4 times 2.5 is 10 joules. This is also my change in kinetic energy. So my kinetic energy initial is 0 joules. My kinetic energy final is going to be 10 joules. The next thing I'm going to do is rearrange my kinetic energy equation for velocity. First, I'll multiply both sides by 2, which would give me 2k divided by m. Take the square root. Therefore, velocity final, which is what I'm looking for, 2 times 10 joules over 5 kilograms, gives me 2 meters per second, which is my VF. Just a quick side note, I also could have done this in one shot. Recognizing this relationship here, if I did force times displacement equals 1/2 m VF, because kinetic energy final squared, I literally could have rearranged this. And I'll get 2 force parallel delta D over m. This would be my work with the individual variables, and I would still get 2.0 meters a second. So this is a technique that's going to be really important a little later. I kept it pretty simple for now. You could find the work right out because I gave you the variables. Understanding that work represents the transfer of kinetic energy into the object is important. Then you can use the kinetic energy formula to solve for velocity. Or sometimes you're missing the mass, you need to solve for that. But one thing I want to introduce early is the idea of transfer, because that is where most of your energy understanding needs to be and what you will be assessed on more than anything else in this topic. All right, I'll end my video on kinetic energy here. Have a good day. This is Mr. M signing off.